Hi, and welcome. My name is Joseph Gao. I'm the Senior Director of Product Management at Rambus, responsible for the secure provisioning and key management solutions. Today, I'll be talking about securing the semiconductor supply chain. The level of awareness of supply chain risks is rising, and threats are being seen on many fronts. Counterfeit parts being detected in military programs, the Semiconductor Industry Association has reported instances of counterfeit parts being detected in critical systems such as medical devices, transportation, critical infrastructure. Estimates of the scope of counterfeit semiconductors ranges anywhere from $75 billion to $170 billion being detected. The scope, scale, and urgency of the problem are getting the attention of industry and government alike. Industry groups and government are responding and working together to address the risks throughout the semiconductor supply chain. Countries, including the US, recognize the importance to national security and critical industries of combating risks in the supply chain. Efforts by industry groups are helping to focus on the root causes of supply chain threats and provide traceability from design through manufacturing. These efforts are being supported by government and are drawing broad participation from leading companies. The semiconductor supply chain is both multi-tiered and complex. Securing the supply chain starts early in the SoC design process to provide the security assets which are the foundation of chip as well as supply chain security. The integrity of the chips and the devices they go into has to be secured from the foundry through testing, packaging, and distribution. As security concerns are becoming a critical issue in market segments such as automotive, defense, healthcare, the call for a trusted semiconductor supply chain is coming from all corners, including device makers, system integrators, service providers, end users, and governments. Securing the supply chain is a global challenge. IPC, the Global Association for Electronics Manufacturing, recently reported the U.S. semiconductor industry is the global market share leader with an almost 50% share. But 70% of all electronics are manufactured in Asia. The U.S. share of semiconductor manufacturing fell from 37% in 1990 to just 12% today. The U.S. share of PCB production has decreased from 30% to 5%. The number of U.S. PCB companies decreased from 1,500 in 2000 to less than 200 today. Electronics products are reliant on electronic manufacturing services. However, today only 4 of the top 20 EMS companies are in the U.S. So given the global nature of the semiconductor supply chain, there is a need for greater visibility and transparency to ensure the quality, performance, security, safety, and trust in semiconductor devices. The consequences that can arise from an insecure supply chain are real and pervasive throughout the electronics value chain. At the chip maker tier, starting at the design level, there are concerns with IP theft, reverse engineering, again leading to economic loss. In the manufacturing process, overproduction of chips in the test and packaging, gray market parts where functional, performance, reliability, safety concerns can start. In the distribution tier, the creation of clones or malicious code being inserted. At the device maker level, counterfeit devices, where there are non-authentic chips available, there is always the risk of counterfeit devices. At the EMS level, tampering or modifying with the devices. In field, malicious attacks on services, such as the distributed denial of service, or attacks on devices and the data it generates. And even at the end of life, when chips can potentially be recycled and put back into use well beyond their useful life. At all stages of the chip lifecycle, it's becoming increasingly critical to ensure supply chain integrity as the risks go beyond just economic and include the performance, safety, security of almost everything that makes up what has become a digital economy. To ensure a trusted supply of semiconductors, there are some critical needs that must be addressed throughout the supply chain. Chips must have a trusted identity. There needs to be traceability of the provenance of a chip throughout the supply chain. There needs to be authentication available at any stage of the value chain. And the chip should be able to attest to critical identifying information. The solution, though, goes beyond the design and manufacturing worlds and extends into considerations of how, at an ecosystem level, the integrity of a supply chain can be monitored and ensured. To make a trusted ecosystem work, there must be some additional considerations. Activation and enrollment of a chip in the supply chain verification ecosystem. The ability to support chip verification for extended domains of trust. The ability to transfer trust from manufacturing identity to device identity, and potentially even to a service identity. There needs to be the ability to support secure onboarding to manage services, such as device management and monitoring. It is the collaboration of the manufacturing world with the consumers and manufacturers of electronic devices that is needed to ensure that our microelectronics industry can be trusted. Now, I'd like to shift gears and talk a little bit about the Rambus supply chain security solutions. Securing the supply chain begins in the design and manufacturing of chips. One of these critical processes is secure provisioning at the manufacturing stage. So, what is secure provisioning? So, secure provisioning is a set of specialized tools and processes that enable high-value data such as keys, device IDs, certificates, feature settings, etc., to be securely programmed into SoCs and devices during manufacturing. It interfaces with the root of trust IP on chips and devices to enable secure storage of provisioned data. It provides evidence of provisioning and interfaces with key and certificate management services to enable identity assurance. So why does it matter? It enables the security features of SoCs, which are usually dependent on the provisioning of device unique key material. It protects costly SoC IP throughout an insecure supply chain. It provides the basis of trust of devices, their identity and provenance in the data they generate, and supports in-field trusted device management, services onboarding, secondary provisioning, feature enablement, cloud security services, etc. The Rambus Crypto Manager platform is a leading secure provisioning solution in use by some of the largest semiconductor companies. Some we've announced include companies like Qualcomm and Micron. It provides solutions for both manufacturing provisioning as well as post-manufacturing key and certificate management services, and these are delivered as a cloud service. The scope of the Crypto Manager solutions address the need to securely insert high-value assets and data into chips at any stage of the supply chain, and also enables the provisioned assets to be leveraged throughout the chip lifecycle to secure devices, data, and services. The Crypto Manager secure provisioning platform consists of three primary components. The Crypto Manager root server. This is the system root of trust. It manages and creates high-value keys. It's typically kept in a secure facility and is used to authorize all provisioning activity. The Crypto Manager Control Center. This is the administrative node, typically resides in the customer data center, that is used for monitoring and managing all of the provisioning activity across all of the manufacturing locations. And lastly is the Crypto Manager Provisioning Appliance Clusters. These appliances are tamper-proof physical HSM-enabled devices that connect directly to testers in the manufacturing facility or to a device over the cloud. And it is used to actually deliver the secure payloads through the tester to the chips. And so currently there are over 2 billion chips being provisioned every year using the Crypto Manager platform. The system has been engineered to ensure keys and data are protected from creation to transit to insertion into chips in a manufacturing environment, especially in environments that are not intrinsically trusted. The components of the system and the workflows it enables have been designed to eliminate risks from people, networks, and purposeful attacks on the provisioning process. All key material and cryptographic processing are contained within the secure boundary of the HSM, or the hardware security module, in the provisioning components, and all communications between the system components and between the provisioning platform and the testers or programmers in the manufacturing environment are protected through strong authentication and mutually authenticated transport security. It has been in full-scale production with our customers for more than 6 years. All components of the CryptoManager provisioning infrastructure are built on a common platform. These are physical servers, enterprise-class server devices with a high-density storage subsystem, and all components contain a physical hardware security module. The operating system is a hardened Linux operating system that also provides health and performance monitoring. And the appliances, the devices that go into the factory, support remote management, clustering and load balancing, failure recovery, logging and audit, as well as providing diagnostics and tracing. The components of the system work together to support a broad array of provisioning use cases for keys, certificates, and protected data. The primary functions of the CryptoManager provisioning platform are, first, injection of keys, certificates, and data into chips. The security of the provisioning process is assured by the platform and is not dependent on vesting trust in the environment in which it operates. Through a trusted manufacturing process, by extension, the identity of the chips and traceability of the process details can also be trusted. This is fundamental to device security, identity assurance, and ultimately supply chain integrity. Secondly, CryptoManager provides a cloud-based key management system to enable the identity and provenance of chips to be validated at any point throughout the value chain. Using the trusted identity established in manufacturing and device-unique cryptographic credentials securely provisioned to the chip in manufacturing, robust authentication and attestation then can ensure consumers of the chip, as well as end customers that depend on them, that the origin and characteristics of the chip are authentic. The following diagram illustrates the overall system architecture of the CryptoManager provisioning platform, as well as the provisioning workflows it enables. So the provisioning process starts with the CryptoManager root server. This is where key material is either generated or imported, as well as where provisioning instructions are signed and authorized. All of this data is securely packaged and transferred to the CryptoManager control center. The control center then pushes this encrypted data down to the CryptoManager appliance clusters in the production facilities. These appliance clusters interface directly to the tester or programmer over a local network. It is the tester or programmer and the test methods that run on these devices that initiates the provisioning process. It sends a request to an API exposed on the CryptoManager appliance cluster, and the CryptoManager appliance cluster then verifies the transaction, performs the provisioning process, and then generates a secure log of the activity that has occurred. These log material is then pushed back up to the control center, where it is aggregated and made available over interfaces so it can be consumed through the rest of the organization. Also, the CryptoManager control center pushes that same key material that was pushed down to the factory up into the cloud, so that when the provisioning transaction is completed, as I said, and the log files are pushed back up into the control center then pushes evidence of that secure binding, that is, the binding between device unique key material and the identity of the device, up into the cloud. This could be the form of symmetric keys in a database of keys, or it could be in the form of digital certificates. Okay? So once the device is trusted, meaning it has key material, it has an identity that's trusted, they are cryptographically bound, now the opportunity exists to provision additional data or keys to these secure devices in the field. So this could take place by one, hosting another cluster of appliances in the data center, where then the devices could come over public networks directly to the API exposed by the CryptoManager appliances and verify the identity of the device and perform the provisioning transaction. Also, the Cloud Key Management Service can perform the same function. First, again, verifying the identity of the device through its key material and through its identity, and then creating a secure session and pushing secure data down to these devices. The system has been designed to secure chips from the earliest stages of the manufacturing process throughout the full life cycle of the devices and services they enable. The system architecture provides the flexibility to leverage the trust established while chips are still on the wafer, and to bootstrap this trust for additional secure provisioning further out in both the supply chain, for example, at a device maker, or in field, as I've shown here, to trusted devices in the field. This allows us to provide the infrastructure and services required to enable the identity and provenance of these chips to be validated at any stage. Again, using this secure identity, which is trusted, cryptographically bound to key material known to cloud key management services, can now execute authentication protocols and attestation protocols to verify the device. Some of the common use cases enabled by the CryptoManager secure provisioning platform and cloud key management services include device personalization, assigning unique identifiers, device identifiers, manufacturer identifiers to the chip, provisioning the unique key material, as well as potentially device certificates to the device, and manufacturing class keys or certificates, and the trust chain to validate them. Again, a rich set of credentials to provide an identity to the device. It provides an audit and control mechanism for production, enabling you to authorize a specific number of provisioning transactions, as well as create and capture and encrypt data from the manufacturing environment that provides proof of provisioning in terms of the activity that has occurred. It enables you to control feature and chip state configurations, that is cryptographically control, as well as audit SoC feature settings, rather than setting a block of static fuses, which is going to control the characteristics of the chip. These can be set through dynamic controls, which are cryptographically gated. Also, you can similarly manage transitions of the lifecycle states of the chip by transitioning them through provisioning transactions. An example of a manufacturing environment configuration setting would be debug or test traces, like a JTAG port, to unlock or lock that during manufacturing as needed, again, using a provisioning transaction. Device certificates can be provisioned, and also their lifecycle can be managed. Whether the key pairs are generated on chip by the CryptoManager platform or even by a trusted third party, any of those models are supported, allows us to push those private keys securely down to the chip and bind the public key material in the form of a certificate to the chip data. The certificates can be generated and signed in line to the manufacturing process, and or certificate delivery as well as associated key management services can be performed through the cloud key management platform. An example of this would be verifying the identity and provenance of the chip at some stage in the life cycle of the chip. Revocation and reissuance of certificates is also supported in the form of lifecycle services. The value that the CryptoManager secure provisioning and cloud key management solutions deliver is well aligned with the challenges of securing a complex and distributed supply chain. Identity assurance of chips and components is the fundamental enabler to securing electronic devices. The factory to cloud and cradle to grave assurance of chip identity addresses the first order security fundamentals. By further enabling the assurance of the provenance, characteristics, and origin of the chips, the integrity of the supply chain that delivers these chips to device and component makers can be verified and assured. Extending the value of securely provisioned and trusted chips to the full ecosystem requires a service delivery model and extended trust domain with global reach. The CryptoManager Cloud Key Management Services supports the use of device unique keys and certificates and provides cloud-deployed APIs that provides cryptographic processing as well as the business logic-specific supporting services to enable ecosystem-specific device and data security. The ability to robustly identify and verify chips also makes possible the post-manufacturing provisioning of application or ecosystem-specific credentials to connected devices. This secondary provisioning may take the form of, for example, certificates and tokens to enable trusted services onboarding, firmware or application updates, or configuration changes and feature enablement. These services, which build on security investments made in manufacturing, make possible key material as a service, which benefits end users, but also enables semiconductor manufacturers and device OEMs to build new services based on business models to monetize the trust that has been enabled in manufacturing. A key aspect of the Crypto Manager platform is the ability to bridge the divide between secure manufacturing and cloud-based security and key management services. As an example of this, I'm showing here a use case where symmetric key material is securely provisioned to a chip in manufacturing. The encrypted key material is pushed from the Crypto Manager control center to the provisioning appliance on the factory floor. In parallel, the raw key material is also pushed to the cloud key management platform and securely stored in a key database. The keys are then provisioned to the root of trust on the chip, where they're decrypted and securely stored on the chip. The identity of the chip is then cryptographically bound to the key material through a hash of the ID and key material that is created by the device and then returned to the provisioning platform by the tester. The provisioning platform then pushes the evidence of this binding to the cloud platform, where it is indexed to the identity and key material of the device. This is now the foundation that enables a chip to engage in an authentication protocol with the cloud APIs at any time to verify its identity, and also to attest to any information readable by the chip, which is not itself intrinsically trusted. An example of this could be firmware version, geolocation, manufacturing process identifiers, network interface parameters. Any data the chip can actually read, it can then encrypt with unique key material to verify the authenticity of that data. This type of multi-factor platform identity assurance is becoming the norm rather than the exception in onboarding devices to high-value services and ensuring the content and integrity of data generated by connected devices. By seamlessly integrating the secure manufacturing process with cloud security services enablement, the Rambus Crypto Manager solutions provide ecosystem-wide ability to ensure supply chain integrity. This is the fundamental element of ensuring supply chain integrity. In cases where trust chains are rooted with a third party, such as common to ecosystems that leverage digital certificates as the primary form of identity assurance and device security, this provisioning and cloud integration remains relevant. Whether public-private key pairs are generated in crypto cores on the chip, a puff on the chip, or by the provisioning platform, certificates can be created, signed, and provisioned on the manufacturing factory floor. And as with the symmetric key material example we just talked about, the public key certificate and supporting trust chain for the device are uploaded to the cloud key management platform and then used as the primary credential in ensuring the identity, provenance, and classification of the device. This bridging of the manufacturing world with the cloud security services that support the device throughout its life cycle are fundamental to a world where everything is connected and few things are trusted without verification. It is these cloud security services that unlock the potential of identity assurance as a core tenet of supply chain integrity. From an architectural perspective, the Crypto Manager Cloud Key and Certificate Management Services provide a clean divide between application services and protocols that are exposed through the API gateways and the back-office data management, cryptographic processing, and business logic technology that supports them. This, by design, makes the services platform readily extensible to support new use cases and device protocols. It also enables multi-tenancy of the service platform, clean separation of tenant assets and keys, and accelerates the process of onboarding new manufacturing facilities and device populations. This illustrates a key point that I wanted to get across in this presentation, that while ensuring the security of the provisioning of chips and devices in manufacturing is a critical step in securing global supply chains, it is equally important that these credentials can be operationalized at a scale and reach that serves the need of the full ecosystem they're a part of. It is the combination of these that are required to address the many challenges of instilling and verifying trust in silicon-based systems. As a mature provisioning and key management platform, the Rambus Crypto Manager solution is unique in the global semiconductor world. It's proven in very large-scale manufacturing environments. It offers simple and minimally invasive deployment into existing facilities, does not require costly secure facilities. A single cluster can support 100 or more testers and provision over 1 million chips per day. It supports system-wide redundancy and disaster recovery. The inventory and keys and data to be provisioned is centrally managed and automatically updated across all provisioning nodes, and alerts and alarms notify operators of any system health or provisioning disruption issues. The system is designed to operate securely in untrusted environments. All the Crypto Manager equipment contains physical hardware security modules. All keys and crypto operations are exclusively done within these HSM boundaries. The connection to testers and programmers is mutually authenticated and secured, and high-value keys and data are never accessible to operators. The system provides broad use case support, whether self-generated or third-party keys, certificates, provisioning of data. All of these iterations are supported. It supports high-performance data transformation inline during the provisioning process. For example, device key derivation, certificate creation and signing, etc. These types of operations can be provided as part of the provisioning protocol. It allows you to provision to the tester or directly to the chip without requiring either to be customized. The secure manufacturing operations, as we've discussed, is tightly integrated with cloud key management services. Device keys and certificate lifecycle management are supported from factory to the cloud. Automatic upload and validation of keys, data, device bindings, certificate signing requests, etc. The upload of this data from manufacturing to the cloud KMS is an automated process. And secure device updates in the field or security feature activation in the field can be delivered as a cloud service. To summarize, I would stress a few simple points that I would assert are foundational to ensuring and verifying the integrity of the semiconductor supply chain. First, trust starts in the semiconductor manufacturing process. The level of trust throughout the lifecycle of a chip will only ever be as good as the trust of the identity and credentials provisioned to the device during manufacturing. Second, secure provisioning alone is not enough. The trust established in chips during manufacturing must be operationalized through widely available services and readily extensible throughout the full ecosystem and domain of trust in which that chip is going to live. And finally, the secure microelectronic devices that make up the fabric and lifeblood of the digital economy are being held to a higher standard as the semiconductor industry matures and continues to grow. It is these elements of a trusted identity, device and data security, services onboarding and registration, identity audit, transfer of ownership and trust, firmware and application verification, and supporting secure secondary provisioning of data, keys, certificates, tokens, device configurations, supporting secure secondary provisioning in the field. It is these attributes that collectively enable a supply chain that can be trusted to meet and safeguard the needs of the new digital economy. So I thank you very much, and I look forward to taking your questions. Thank you.